Okay. I think maybe we can start and people will just kind of file in, if that's okay. So let me start by introducing the speaker, if that's okay. So good morning, everybody. Today, Professor Wendy Freedman will be speaking at the APCTP Colloquium. So I'll introduce the speaker very briefly. So Wendy started her career at the University of Toronto, receiving a doctorate in astronomy and astrophysics. And then she spent much of her career at Carnegie Institution of Science, where she became the director of the observatories. Wendy is currently a senior professor at the Kavli Institute for Cosmological Physics in Chicago. So we have a bio. You have a huge list of achievements. So I'm only going to include some of them because I don't want to speak for very long. So a list of her achievements includes winning the George Lemaitre Prize in 2024, the Gruber Cosmology Prize in 2009, the Magellanic Premium Award in 2002, and she has been the PI of the Carnegie Supernova Project, the Hubble Space Telescope Key Project, the chair of the Giant Magellan Telescope Project, and served as chair of the Astronomy and Astrophysics Advisory Committee in the US. And also I checked the speaker's Wikipedia page, and she has an asteroid named after her, which is really cool.
I didn't realize that was there. Okay.
It's true. I don't know if it's true because Wikipedia,
It is true.
Okay, that's really cool. But anyway, we're very happy to host Professor Freedman, and today she's going to talk about the standard model of cosmology. So please start when you're ready.
Well, thank you very much for the invitation to speak, and good morning to everybody. Good Friday morning, and it's Thursday evening for me here in Chicago. And it's a great pleasure to share with you some recent results from the James Webb Space Telescope and the implications for the Hubble tension, which probably most people are aware of. I'm going to give a status report today. Of course, I'm not going to resolve this tension, but we're making enormous progress in being able to measure very accurate distances to galaxies. And what has made the difference are two things, really: the Hubble Space Telescope and most recently, the James Webb Space Telescope. And I will describe to you the number of methods that we're using to measure distances to nearby galaxies and how those have improved, and then where the current challenges still reside. So we have this standard model, and appears to fit a lot of data really well. But one area where there seems to be some discrepancy or tension is the measurement of the Hubble constant, and the difference between what is being inferred from measurements of the cosmic microwave background and the local measurements based on Cepheid variables. So what we set out to do in the Chicago Carnegie Hubble program is to measure the distances to nearby galaxies that set the calibration for the determination of the Hubble constant, and do that measurement not simply with Cepheids alone. Cepheids have become the de facto standard for measuring distances. They've been used for the extragalactic distance scale since the time of Henrietta Leavitt and Edwin Hubble, and we understand them reasonably well. But any method will have its own systematic uncertainties, and that those kinds of uncertainties are really what have plagued the distance scale for the 100 years that we've been measuring distances in astrophysics. And so the idea is to use different methods, but apply them to the same galaxies. And that hasn't been done before, where you're using the same equipment, essentially, where you can make a reasonable relative comparison. So we've been developing another method that makes use of red giant branch stars. These are bright evolved stars. Our sun will eventually become a red giant. And it's a phase of their evolution where they have a constant luminosity, as I'll show you in greater detail. And a third method that uses a kind of carbon star, which we're referring to as JAGB, or asymptotic giant branch stars. And so the idea, again, is to measure these in the same galaxies. We have now almost 10 times the sensitivity of Hubble at near infrared wavelengths, where we're measuring these objects, and almost 4 times the resolution. So it's a big step in capability. And what we do is we tie into type 1a supernovae, which are these explosions, of course, that you can see almost over the entire extent of the visible universe. And we apply this locally where the Hubble law hasn't yet begun to turn over because of the effects of dark energy and the acceleration. But the idea, again, is to use 3 independent methods. We then calibrate the type 1As, which on their own, we only measure relative distances to the type 1A supernovae. There are none that are close enough to anchor them, say, to a method with geometric parallax, but we can anchor them in a realm, an intermediate distance range, where we can measure all 3 of these methods and determine their distances independently. So for any of you who are interested in the details of how we make these measurements of distances and how those measurements have continued to improve as we have had data that allow us to correct for the presence of dust that have multi-wavelength capability, and then getting above the Earth's atmosphere with the Hubble Space Telescope. And we put a lot of work into refining the Cepheid distance scale before the Hubble Key project, before Hubble was launched, and continued to move into the infrared as infrared detectors became available on Spitzer and Hubble. And similarly for the tip of the red giant branch, and how we can measure this luminosity of these stars as they undergo the core helium flash, which I will describe more in a moment, and these AGB stars, asymptotic giant branch stars, that are even brighter yet than the tip of the red giant branch. So 3 independent ways of measuring these distances. Now, there are many challenges in measuring the Hubble constant. We've seen a lot of these over many decades now. And perhaps most well known is the factor of 2 debate that was really unable to be solved in the 1970s, 80s, up until 1990. And there were 2 major groups, one that was Alan Sandage and Gustave Thomon, and then Gerard de Vaucouleurs. And de Vaucouleurs was getting a Hubble constant of about 100, and Sandage and Thomon were getting values closer to 50. And the error bars in each of these cases were smaller than or comparable to the size of the symbol shown here. And so there was no overlap at all in the uncertainties. And that was resolved when we did the Hubble Space Telescope Key project, when we were able to finally get above the Earth's atmosphere, and we had linear detectors, that is CCDs, flown on HST, where we could get more accurate photometry and correct for some of the systematics that had not been essentially paid attention to in this era, simply because you couldn't with the data that were available. And now here's where we are, just shown by these 2 red lines. So the Hubble Key project got a value of 72. And today, what we're looking at, what is given rise to this tension, is a value between 67 and 73. So the 67 is coming from what is inferred from measurements of the cosmic microwave background. So fluctuations in the temperature and the polarization. And then the value at 73, and I seem to have lost my cursor, here we go, comes from primarily from the Cepheid calibration and the work of the Shoes group. And it's not now simply that there's this difference, but what is being claimed is that we have uncertainties that are given by the width of these lines. So that is, these are so well determined that it leads to a 5 or 5.8 sigma has been claimed recently, discrepancy between what you infer from the microwave background and what you measure locally. So the real challenge now is to ascertain whether the systematics that could potentially affect these measurements are small enough, that is, the microwave background measurements have a precision of better than 1%. So in measuring the local distance scale, the bar now has been set very high to measure distances to less than 1% and ascertain if this discrepancy is real. That is a very tall order. It's never been done before with photometry at these distances, and whether or not systematics yet have been minimized to the point where you don't have systematics that are dominating, as has been the case historically in the distance scale. So this is an obvious point, making a distinction between precision and accuracy. And often it's referred to this past decade as the era of precision cosmology, and that's certainly true. We're making more precise observations, but of course, what we want is an era of accurate cosmology, and that's a harder, that's a much taller bar to get over. Here's an example of the types of systematics that plagued the early measurements of the Hubble constant by Edwin Hubble himself and Alan Sandage and de Vaucouleurs, for instance. The photographic plates that they were using at the time, the detector, astronomical detector at the time, was sensitive to blue wavelengths, but not infrared or redder wavelengths. And it wasn't until we got CCDs in the 1980s where we were able to make measurements from the blue into the near infrared. So this is the B band at about 4,500 angstroms and the I band at about 8,000 angstroms. And so when I made these first measurements and measured apparent distance moduli, not in that order, there was considerable scatter. But what was immediately apparent was that it wasn't just random, but that if you used an interstellar extinction law, that is the behavior of dust in our Milky Way galaxy that had been measured in many different regions, then they fit the data really well, and you could extrapolate to long wavelengths where you could measure the true distance to the galaxy unimpeded by dust. And as we got Spitzer data later in 2009 or so, we could extend out to even longer wavelengths. So this is inverse wavelength shown here. And at longer wavelengths, you are approaching the true distance modulus to the galaxy, even in regions where you have a lot of extinction. And you can see it's fairly well behaved. Sorry, this is moving backwards. And so when we went to do the key project, we didn't have copious amounts of time on a very oversubscribed telescope. And we used V&I photometry and later tested that with infrared photometry when there was an infrared camera on board. So one example of systematics. Here's the final result that we got from the key project. This is velocity as a function of distance, exactly as Hubble originally plotted the data when he discovered the expansion or discovered the relation between velocity and distance that bears his name. He remained skeptical till he died about whether or not it was actually indicating an expansion of the universe. But his original data fit into this first tick mark here on this plot. So it's now possible to make measurements of distances at far greater distances. And with the key project, our proposal was to use 5 different methods, secondary methods, for measuring the distances beyond the realm of the Cepheids, and to use Cepheids again as the nearby galaxies that set the 0 point. Now, you can see, so this is now showing a projection about this fit to a Hubble constant of 72. You can see that the type 1a supernovae shown here in green extend out the farthest. They are very bright objects, and they also have very small dispersion. They're not affected in the same way by peculiar motions of galaxies. So that is, in the nearby universe, the galaxies tend to be clustered. They're in groups and clusters, and they induce peculiar velocities into the motions of the galaxies themselves. So as you go to greater distances, and therefore greater velocities via Hubble's law, these types of peculiar motions, which may be 250 or 300 kilometers per second, become a small fraction of the overall smooth Hubble expansion, whereas they're a larger fraction for nearby galaxies. So the type 1a galaxies, type 1a supernovae have become the method of choice post-key project because of the small dispersion and the fact that they are so bright. So the key project resolved the factor of 2 debate. And I'm showing here, these are measurements of the Hubble constant as a function of time. So here's our key project value in 2001. And the points in red here are values of the Hubble constant that are based on the Cepheid period luminosity relation and extending farther out using these type 1a supernovae. And all the other published values in the literature are shown here in blue. This was a database that was started by John Huckra before his death, and then picked up by Ian Steer. And you can see that the values that have been obtained using the Cepheid calibration lie high with respect to all of these other measurements. So that may be real, but it's also something that we wanted to look into. I've spent a lot of my time measuring Cepheid distances, and this is a concern that maybe there's some systematic with the Cepheids, and if all you're using are Cepheids, then you're not going to uncover that systematic. So that again was motivation for developing these other distance indicators and for measuring the Hubble constant independently using very different methods with different systematics. So again, probably everyone is familiar with the Planck results. Here's the 2018 map. These are the temperature differences across the sky, and you can compute spherical harmonics and plot here the power spectrum of the fluctuations in temperature shown here, and this is temperature across the E-mode polarization measurements below. And with a 6-parameter fit, you can see it's an exquisite fit to the data. I mean, it's really quite striking now, the number of peaks that have been measured and how well this 6-parameter fit or a lambda cold dark matter model fits the microwave background data, both for temperature and for polarization. So this is a prescriptive model, and it then you can infer what the expansion rate would be today, given this model, which has dark matter, dark energy, and you the result is a value of the Hubble constant of 67.4 plus or minus 0.5, so better than 1% precision. And that's now what, of course, people refer to as our standard model, and that's a model that's been around for now about a quarter of a century, but really, I think, illustrated beautifully with the microwave background observations. Here now is a comparison. So again, here are the Cepheid measurements, the calibration of the Hubble constant based on Cepheids. And here now showing the measurements that come from the CMB, first from the WMAP probe, Wilkinson microwave anisotropy probe. Here are the Planck data, and here's another measurement by the Atacama Cosmology Telescope plus WMAP. So this is where the tension that people talk about has arisen between the Cepheid base measurements and CMB. And then we set out in 2019 to calibrate the distance scale using the tip of the red giant branch. And we were hoping to resolve the difference to find either one or the other, and we landed essentially in the middle. So in good agreement with the CMB, you wouldn't need to invoke the existence of a Hubble tension and some other missing fundamental physics from the standard model, but almost equally in agreement with the Cepheids themselves. So it's one of the things that I wanted to make a distinction. There are two tensions. One is between the Cepheids and the CMB, but there's also between the TRGB calibration and the Cepheid calibration. And this is interesting because it's only in the last month or two we have found convergence between the Cepheids and the TRGB, but not yet convergence in the Hubble constant. So really interesting and important progress on the distances, but we're still seeing that there is a discrepancy in the Hubble constant. This is just a recent compilation of measurements from the new DESI results. These are measuring the baryon acoustic oscillations, so the matter spectrum, and similar to the CMB in radiation, but measuring as a function of redshift, which you can do with the BAO measurements, what the fluctuations in the matter density are. And the interesting thing about these observations is several years ago, most of the BAO measurements were calibrated using the CMB itself, because you need some way to anchor it, just as we do locally for the Cepheids. You need a 0-point anchor, and you also needed an anchor for the BAO measurements. And so they would use the CMB, the sound horizon. And now you can do this completely independently of the CMB, and particularly interesting is using Big Bang nucleosynthesis observations. And so here are the DESI results shown here for different adding in different data sets. And so those are giving a low value of the Hubble constant, similar to the CMB measurements. This is now comparing with, they've compared their results with ours from JWST, and then the shoes measurement, which is more of an outlier in this comparison. So I think we're reaching an interesting junction because we have now several different ways of doing this, and they're still not agreeing. And so getting to the bottom of this disagreement, is it fundamental physics or is it something still that we don't understand in the measurements? And it's not for lack of trying that people have been very creative and tried to understand what could explain this Hubble tension and early dark energy, late dark energy, and so on. These are some of the kinds of models that have been proposed. But as we saw from the microwave background measurements, the peaks in the acoustic spectrum now are so tightly, well measured that most of these other ideas just don't work. They're in conflict with other data, BAO or the CMB measurements themselves. And so I'd say the best candidate at the moment is what people refer to as dark energy, early dark energy. And that's where it's posited that you would have a scalar field sometime before recombination that would increase the expansion rate, but it would have to disappear before recombination so that you're not affecting the late time peaks. And so I think what's interesting about early dark energy is that very soon the Atacama Cosmology Telescope ACT is going to have polarization results. They were seeing in their early data release a small little peak that was at almost 3 sigma, and that is either going to come through as a booming 40 sigma signal, or it's going to be clear that it's noise, and that that would be very interesting. So the early dark energy comes with 3 additional parameters, so 9 parameters, excuse me, would be needed to describe the cosmological model. But despite all of these really valiant and creative efforts, no convincing explanation has been found for this Hubble tension. And in fact, if you have early dark energy or some of these other explanations that have been proposed, you actually make the tension with the matter density fluctuations worse, the sigma 8 parameter. And so you increase the size of the uncertainties, you've added extra parameters, you worsen another tension that's seen. You might reach 70 or 71, but no models have reached 73 or 74. So in essence, it's been very difficult to find an explanation for this Hubble tension and in terms of theory. Maybe yet to be found, but not so far, despite a lot of effort. So here are our group, excuse me. And by choice, it's a very small group. I've worked in big groups, I've worked in small groups, and this is one I really enjoy working in. I actually get to work myself. 2 graduate students, Kayla Owens, Abby Lee, and 2 postdocs, Taylor Hoyt and In-Sung Jang, and my long-term collaborator, Barry Medor. We posted 2 papers so far. There is another one coming, I hope, in a week or 2, and several others in preparation. So what are the current challenges in measuring the H0 value locally in a more accurate way? Now, we can't do this in one step. As I said, the type 1a supernovae, they are too rare. They haven't occurred in near enough galaxies where you would have possibility of making geometric measurements. It would be difficult to do for supernovae anyway, as they explode. But so there are 3 steps. One is the anchor galaxies, and that is where we use geometric techniques in the Milky Way, for example, measuring the parallaxes of Cepheids. In the Large Magellanic Cloud, there are detached eclipsing binaries, and NGC 4258. Really sorry. There are there's a mega maser. There are masers, water masers that are orbiting this galaxy. And you can measure both proper motions and radial velocities, and also obtain essentially a geometric measurement of the distance to the galaxy. So 3 and maybe 4, the Small Magellanic Cloud also can be included. Then we step out to the realm of the Hubble Space Telescope and James Webb. And here's where we can measure Cepheids, and here are tip of the red giant branch stars, and now JGB stars. in galaxies that have had type 1a supernovae. So we measure the distances using these 3 different techniques now. They've all had type 1a supernovae. That then calibrates the Hubble diagram for the type 1a supernovae. So I'd like to just point out, while I have this image here, one of the nice things about the tip of the red giant branch method. Here we can measure individual red giant branch stars in the halos of galaxies. They're away from the dust in the disks of galaxies, and they're not crowded. And the Cepheids are more challenging because they are young stars. We find them in near spiral arms in the galaxies, near to the regions where they formed out of the dust and gas clouds that collapsed to form the Cepheids in the first place. They haven't had time to diffuse away from these regions of star formation. So at the high surface density, they're contaminated by the light from other nearby stars. So extracting the luminosity of the Cepheid itself has some challenges. There's dust, which is a challenge. They have differences in metal abundance, and they also have a temperature dependence that is correlated with their colors. So there's some degeneracies that it's more challenging to make these measurements. And supernovae are rare, so there are only a few dozen galaxies nearby enough where the type 1a supernovae have gone off. And that, I think, is emerging as a place now where the uncertainties are still large, and we need to increase that sample. The difficulty is we only get about 1 or maybe 1 a year, 1 every other year of a supernova in a galaxy near enough to make these measurements with the other methods like Cepheids or tip of the red giant branch. So it's going to take a while to build up the sample, but that's coming. Now, let me just show you a comparison of fields that were observed. This is an image taken by the SHOES group in a galaxy at 20 megaparsecs. And here is the Cepheid measured in the H band, or the 160 filter, 1.6 microns. And you can see, the resolution is not very good. The signal noise is not very good. There are other things around the Cepheid. So measurement of these stars is non-trivial. But here's what happens when you go to JWST. So with the 4 times better resolution, 10 times better sensitivity, this is a comparable band, the J band, at 1.2 microns. And you can see how much better and how much more accurately we can make these measurements. I'll point out that about 60% of the sample is located at distance greater than 20 megaparsecs. Those have not been measured yet with JWST. We, in our proposal to JWST, preferentially, what we did was we observed the nearest galaxies where the crowding would be the least, the contamination by other stars, and where they're closer, brighter, and the measurements would have higher signal to noise. Here's another example, again, same galaxy, only at 20 megaparsecs. This is what it looks like with Hubble, and here it's what it looks like in the near infrared with JWST. So, and just to point out that, so the calibrating galaxy NGC 4258 that has the megamaser, it's at a distance of 7 megaparsecs. So there's 8 times larger area that's being covered in this red circle than at 7 megaparsecs. And at 40 megaparsecs, it's 33 times the area. So again, 60% of the galaxies lie at greater distances than I'm showing here, and 25% beyond 40 megaparsecs. So these crowding issues, I think, are something we still have to pay attention to. And here just some more examples. I'll go quickly to, in interest of time, but here are the Hubble measurements of Cepheids in a number of different galaxies. And here are the JWST observations. And these last 2 columns are the V and I, or measurements from Hubble. So the crowding is not as bad. Resolution is better in the optical. These are HST observations. And they are still what's being used to measure the corrections for dust. So not as high resolution as JWST offers. I'm going to confine my remarks today primarily to the tip of the red giant branch, because there we can combine our Hubble sample with the JWST sample so that we have a larger overall sample to calibrate the type 1As. But I will say we're finding very good agreement of those distances, TRGB with JGB and Cepheids. I'll show you. So for the first time in this field, we actually did the reduction of the data blinded, the initial reduction. And what we did was we applied random numbers to each of the photometry catalogs. So they're arbitrary 0 points, and we had no knowledge of the distances or the Hubble constant as we were analyzing the data. And so we did all of the quality cuts on the photometry with the plotting of the PL relations for the Cepheids, period luminosity relations, doing artificial star tests, injecting stars with known luminosities, and then measuring those in the same way as we do the program, the target galaxies, measurement of the luminosity functions for the tip of the red giant branch and the JAGB. For the JAGB analysis, nothing was done further to that analysis. So I would say that it was completely done blinded. And the others were almost completely blinded, but we did discover an error in the pipeline of the Cepheids, an additive effect, something that had been added twice, so that had to be added, but it was just an additive correction. And for the tip of the red giant branch, there were some that the size of the region that was being analyzed got increased just to increase the numbers of stars and the statistical uncertainty, but in very good agreement with what had been done before. So, essentially 95% or more blinded the analysis. Here are our program galaxies, and the red squares, if you can see them, sometimes that doesn't project well when in a larger screen. But what we tried to do was to point the camera. There are two cameras on the near infrared camera for JWST, one in the halo where the TRGB stars are, and then another in the disk where we could do the Cepheids in the inner disk, and then these JGB stars are in the outer parts of the disk. And so that they were optimized for each kind of method that we were using. And this is now what theoretically is known as the Hertzsprung-Russell diagram. So this is luminosity increasing up, temperature to the left, and showing the positions of these stars. So this is the observational equivalent. These are the filters that we use on JWST. But the Cepheids here, this is where they reside. They're the brightest of the distance indicators. Here are the JAGB stars, and this is the tip of the red giant branch, which has a slope in the near infrared. But we can do this all together. What's nice is that we're testing completely different types of physical methods. They're found in different environments. Their crowding amounts are different. The dust is different. The chemistry is different. They're in different evolutionary stages. But at the same time, we can take advantage of using the same detectors, the same filters, point spread functions, the software we use, and the absolute calibration. So the comparison then of the relative distances is really meaningful. And just to emphasize the fact that the Cepheids are the most challenging of the methods that we use, simply because there are a number of parameters. There's a color term, which there's an intrinsic color term, which is a manifestation of the changes in temperature as the Cepheid is going through its pulsation cycle. It also, there's a color term you have to correct for the presence of dust. And then there's a metallicity term. So metallicity being anything heavier than hydrogen and helium, which is empirically calibrated, but those are difficult measurements, and there's not good agreement in the literature as to what this coefficient for metallicity should be. This is the oxygen to hydrogen abundance relative to solar. Tip of the red giant branch is simpler. In the I band, there is no slope. In the J band, as I showed you, there is a slope. But it's there's a slope to the period luminosity relation. This is the simpler part of the PL relation. And for the asymptotic giant branch method, the stars have a constant luminosity in the J band. So they're much simpler than the Cepheids. So let me say a few words about the tip of the red giant branch, because this is a method not as well known, I think, to most people compared to Cepheids. These are low mass stars. As I said, the sun will eventually climb the red giant branch after it's exhausted the hydrogen in its core. And so they're 2 solar masses or less, and they have a partially degenerate then helium core. So once the hydrogen is exhausted, they have a helium core, the star collapses, but there isn't sufficient temperature to ignite helium burning. And so there's still a shell then of hydrogen surrounding this partially degenerate helium core, which is powering the luminosity. And so the temperature rises as this hydrogen is being burnt, and then it's depositing more helium onto the core. And when the star reaches a temperature of about 100 million degrees, then that's enough to begin core triple alpha process, essentially, and core helium burning. And the star quickly, because it's degenerate, it can't expand. So it's very quickly rearranges itself and then falls down in luminosity onto the horizontal branch. But what the observational then, what we see is that there aren't stars that climb above the position of this core helium flash. And because this degeneracy is happening at almost constant core mass, then the ignition is occurring at a predictable luminosity. So this is the only method that can be actually predicted from first principles in physics. The Cepheids pulsating, they have not, people do not have models with pulsation that can predict their luminosities, and the JWST stars are also more complicated. So it's a nice method, conceptually very simple. Here is the red giant branch here. Stars ascend the red giant branch, and when they reach a temperature where the core helium flash occurs, that's what we are measuring in the luminosity function here, shown in gray. And we apply essentially edge detection techniques to quantitatively measure the first derivative of the luminosity function. And we do all sorts of artificial star tests and inject things to make sure that we can measure this with precision and to estimate what the uncertainty is. And we've done maximum likelihood fits and these different Sobel filters, but they all are agreeing very well. So it's an advantage of this method, its simplicity. And here I'm just showing some examples of these Sobel kernels that we evolve with the luminosity function. What we're looking for here again is the Hertzsprung-Russell diagram. So here's the red giant branch. Here's the asymptotic giant branch. These stars occur in about a 4-to-1 ratio. So that if we look at the luminosity function, the numbers of stars as a function of magnitude, you see the AGB stars are essentially a pedestal. Then you see this discontinuity at the position of the core helium flash. And then here's the luminosity function for the red giant branch. So we're looking for the first derivative here. And these methods, whether we use maximal likelihood or Sobel kernels, they agree very well. Here are some results from our cycle 1 JWST. And for those of you not used to looking at these types of plots, each dot is an individual star in the galaxy. So again, luminosity up, temperature to the left. And even at a distance, I think you can see that there are more stars on the red giant branch than on the asymptotic giant branch. And quantitatively, we can deproject and measure very accurately the luminosity of the tip in all of these cases. And these are results that we found in our 2019 HST study, where we began to calibrate the galaxies with type 1a supernovae. The points in gray here are observations that were made with telescopes on the ground that had Cepheid distances and tip of the red giant branch distances. So you can see there's very good correspondence. So here you can see the scatter about this. This is just a slope equals 1 line. The scatter gets greater at greater distances. These are the galaxies that have the type 1a supernovae. So without the supernova galaxies, there's only a 2% scatter. But the supernova host galaxies have a larger scatter. And what we found at the time was that our distances from the tip of the red giant branch were in disagreement with the SHOES Cepheid distances by about 0.06 magnitudes, which translates into a 3% difference in distance. And so that is something, what we've now resolved is that we've resolved the distances in favor of this 2019 tip of the red giant branch scale. The SHOES distances now have changed and converged to our original TRGB distances. So that's a big step forward. I'm just showing here the galaxies that we have in common, our own CCHP HST measurements and our JWST. It's a small sample, but they're agreeing very well and formally to better than 1%. So the distances to the TRGB galaxies have held up over time at this 1% level. And if we compare with SHOES, the 2016 SHOES result, which at the time, that's what we had to compare with our 2019 study, there was an offset, and the disagreement was at about a 4% level for the sample shown here. But in the meantime, the SHOES group reanalyzed their data, redetermined their distances, and they're now agreeing with our JWST method measurements at the 1% level. So this is new, and it's, I think, very promising. We're closing in on understanding what is happening. And that's not so. At the same time, the supernova sample, they also reanalyzed the supernova sample, and then the Hubble constant did not change. So there was no intermediate step that showed this 4% offset. Here's a comparison of the absolute magnitudes of the supernovae between their 2022 and 2016 papers. And there is, again, this offset in the absolute magnitudes, which is the quantity, the absolute magnitude of the supernova that sets the Hubble constant. So it's an offset of about 1.7%. And you could see some of the differences in their reanalysis were over 0.3 of a magnitude. That's more than 15% in distance. So some of them were quite substantial. And just for comparison, that amounts to almost twice the size of the Hubble tension. So what these moved by more, the offset was more than the size of the Hubble tension, which is, we're still looking at systematics as being an important contributor to some of these measurements. And now if we compare, here's the whole sample for the tip of the red giant branch that have either HST or JWST measurements for those galaxies that we have in common with SHOES. And you can see, again, so the offset now is only 0.02 magnitudes. That's 1% or so in distance. So it's really very pleasing progress. So the SHOES distances have changed. And so this is just Adam saying now that there is this opportunity to compare the two distances, it produces a very small difference when you're looking at the new data. Anyway, we had a long discussion about the 2019 paper, and anyways, it's very nice to have that resolved. So here is the distribution of the absolute magnitudes, again, based on the Cepheid distances. So the supernova host galaxies, this is the middle rung again. This is the distribution of the SHOES Cepheid absolute magnitudes for the supernovae. And here is the distribution of the TRGB galaxies, which is broadly similar. It's not too discrepant. And just getting ahead of showing you the supernova data, this histogram here shown in blue is from the Carnegie Supernova Project. This is what we carried out at Las Campanas for supernovae at all distances. Here is the calibrators. Obviously, the distant flow sample is much larger. You have much larger volume to survey, and showing again that we do need to get more nearby calibrators. But if we blow up the histogram by a factor of 10 and compare with the Hubble flow, there's no indication that we're not seeing something that is really representative of the Hubble flow. So I think it's a representative sample and a reasonable sample to do the calibration with. One other issue with the small sample and the fact that it gets harder to measure distances as you go farther away, if you divide the sample by the uncertainty in the measurement, so this is the uncertainty that it allows for both the uncertainties in the distances and the supernova measurements. When you have small errors, there's a difference. The distant supernovae are fainter than the nearby supernovae. That gets masked when you're looking at the supernovae that have larger errors. And so I think this is, we're narrowing in on why some of the difference between our two groups has to do with the uncertainties now in the supernova sample, which is still small. And the root end statistics are still, well, they need improvement. And so if we're looking for 4, 5, 6 sigma confirmation of the Hubble tension, I think this is a place that really needs to be improved. So the sample is small, and the galaxies with the smallest uncertainties have systematically brighter magnitudes. What that translates into is a smaller value of the Hubble constant. So we need to understand these sorts of effects, and the sample will need to be improved to do that. I'm going to speed up slightly. I'll tell you a little bit about this new method that we've developed for the carbon J-band asymptotic giant branch stars. These are more massive. They're asymptotic giant branch stars. They have both, they're double shell burning. They have both a helium burning shell and a hydrogen burning shell. And carbon is being mixed up or dredged up to the surface. It's why these stars appear red why they're now great objects to observe with JWST because of its sensitivity in the infrared. And what the models tell us is that for the massive stars, carbon is burned even before it reaches the surface. But for the lower masses, the carbon never reaches the surface at all. So there's an intermediate range in luminosity where we see these carbon stars, these JAGB stars. And it was noticed by Nikolaev and Weinberg now essentially 25 years ago that there's almost a constant luminosity, which makes these ideal in terms of a distance indicator. And so if you measure the luminosity function of these stars, this population, it's very nearly Gaussian, has tails, but the mode of this distribution is very stable. And so this is something Barry Medora and I, sort of during the pandemic, looked at a sample of galaxies that had infrared data. These are data that were taken by others, not for this purpose at all, but that already also had TRGB distances. And so when we compare the TRGB distances with the JGB distances based on the stability of the luminosity of this class of stars, we were really rather astounded at how well they did. And so that was the base. We also looked at, these are ground-based data. We looked at data from Hubble, from the archive, and the method continued to hold up. So when we applied to JWST, we said, okay, this is a new method, but we get it for free and we can test it. And we were getting the data anyways for the TRGB and the Cepheids, and we'll see how well it does. And it's continued to hold up. So we're making measurements of these stars outside of these white contours shown here. Again, we want to minimize crowding effects. And if you look at the luminosity function for these stars, they're very centrally peaked, and we can measure the mode of this distribution and therefore a distance and compare those with the tip of the red giant branch. So here's now the sample of ground-based and the JWST distances and comparing the JAGB and the TRGB distances. So there's excellent agreement. It's in fact better than 1%. So far better than I certainly would have predicted. But these look like really promising distance indicators. Cepheids, we know much more about Cepheids, having studied them for so many years, but I'll just point out that the amplitudes decrease as you go to increasing wavelengths. So this is the ultraviolet here through the K-band at 2.2 microns. And also the dispersion in the period luminosity relation decreases as you go to increasing wavelengths. So these are points that we used in developing the key project for Hubble. And here's another example of how we can correct for dust by getting multi-wavelength data. And here's just an indication of some of the Cepheids that we've been observing with JWST. Some galaxies don't have a lot of Cepheids. Either the star formation rate is low or they're too crowded to work in the inner regions, so we have smaller samples. But this is work by a graduate student Kayla Owens in preparation. So I'll say a few words about the Carnegie Supernova Project. This is a project that Mark Phillips and I were co-PIs on when I was at the Carnegie Institution before I moved to Chicago. And the aim of this program was to measure the follow up on type 1a supernovae that had been discovered with other programs. So the discovery surveys didn't have the time to go off and really get good cadence and multi-wavelength data. They were trying to increase numbers of supernovae. So our program was to observe them before maximum, make sure that they had very good coverage, and do this over a range of wavelengths so that we could correct for reddening, look for metallicity and environmental effects, and also obtain spectra as a function of time, so that you could do the K corrections, the band shifts. With these stars, these supernovae are exploding, and their spectra are changing as a function of time, and so the correction for this band shifting also changes as a function of time. So it's extremely well sampled, both photometry and spectra, and it's the most extensive self-consistent data set for dealing with systematics. And these are the data that we use as input to our Markov chain Monte Carlo analysis for determination of the Hubble constant. And so I think, again, so as we go to this next phase and we want to increase the numbers of supernovae that are calibrating the Hubble constant, we need very well observed supernovae at multiple wavelengths, and to allow us to, if we want 1% measurements, we need data that can deliver that. Here's our Hubble diagram. These are the more distant supernovae in the sample. And so this is a distance modulus logarithmic version of the Hubble constant. And here's the dispersion about this slope 5 line. So there were 2 phases of the project, one in 2004 to 2011, and the other, I think, 2011 to 2015. And so here is the input. We use 2 different MCMC programs, and so the likelihood is given here. There is a stretch we have to correct for the fact that brighter supernovae decline more slowly. It's not unlike Cepheids, the brighter ones pulsate more slowly. And again, a correction for color. And then there's what people refer to as the mass step, a difference in the mass of the progenitor, the galaxy, not the supernova. So that's not well understood, because obviously it's not the galaxy, it has nothing to do with the galaxy, it has something local to do with the environment of the supernova. So there are 8 dimensions in this particular case that I'm showing for the tip of the red giant branch, 30,000 steps with a 33,000 step burn-in. And so the peculiar velocity we adopt is 240 kilometers a second. Again, these are due to the mutual gravitational interaction of the galaxies. And what we're finding is a Hubble constant of 70. And I'm just attaching here rather generous uncertainty. We're still working on the uncertainty analysis. We just combined the sample, so this is new, but we're still finding a value of 70 with the larger sample. The next steps, I think, are clearly we have to increase the numbers of supernova host galaxies where we can measure the Cepheids and other methods with JWST, with these high resolution measurements. And I think we still have yet to demonstrate that the galaxies with distances beyond 30 megaparsecs are not still suffering from systematic errors due to crowding. And one of the reasons that I say that is there's a paper from the Shoes group that says that at 8 sigma confidence, the crowding is not an issue. But as I showed you earlier, the reanalysis between 2016 and 2022 data had these very large offsets. But the 2 galaxies that had the smallest offsets are 2 of the galaxies here that you would expect that these were well measured and didn't suffer from problems that caused these large deviations. This one's even closer, and there's 1 galaxy that's farther away. So I think until we fill in this middle range where the bulk of the sample actually lies, we can't be confident yet, especially as we're trying to achieve 1% to compare with the microwave background. So I think there's still work that needs to be done here. So I'm just going to conclude by saying at the moment we are finding a value near 70 based on these three methods. But at this point, what I've shown you primarily today are the results based on the tip of the red giant branch. And for comparison, this is the probability distribution for Planck, and here now the new DESI results. And so these are really quite consistent. We wouldn't be talking about a Hubble tension. And I think, it's yet to be determined whether there really will end up being a tension that persists. So for me, this is very much like the era with Hubble. When we were able to get above the ground, we suddenly had better resolution, better detectors. JWST is really ushering in a new era of accuracy for these kinds of measurements for the Hubble constant. And the fact that we're seeing these independent distances that are agreeing at the percent level. So our TRGB and JGB stars are agreeing at the percent level. We're agreeing now with the REIST group. That is real progress. But the differences now are surfacing in the nearby supernova sample, not the calibrating distances. So that's very new, and I think it's something we now need to turn our attention to. The errors, the uncertainties in the Cepheid measurements vary by about an order of magnitude. So the weighting is very different where those supernovae are coming into the calibration. And so and so it's not really that there are 42 galaxies and root n statistics. There are, maybe 25% of the sample is dominating. So we need to improve that sample, and that will come because Rubin is going to be discovering many supernovae. There's ZTF that also is discovering more supernovae. The fact that we can use JWST and JGB stars will be able to cover a larger volume where the supernovae can be measured. Both of those methods can be measured in the same galaxies. So that will come within the next few years. I'm optimistic that's going to improve. We still need more JWST data to fill out that sample of the existing supernova galaxies with host supernovae. And we still need to ensure that the more distant ones are not systematically in error. That has yet to be ascertained. So stop here and just say that at the current time, I think we're seeing now real convergence and a Hubble constant of 70. We can't rule out that there is a Hubble tension, but we certainly can't say that our data are pushing us in that direction. If we had used, for example, tip of the red giant branch for the key project, we might be asking the question, why are the Cepheids an outlier compared to the CMB and BAO and TRGB? So I will stop there, and I'm happy to answer any questions.
Thank you very much for a very nice talk, Wendy. Thank you. So now if you have a question, please put your hand up. Or you can just ask in the chat. Okay, so I guess I can start by asking some questions while we're waiting for people. So I have some basic questions. So you said the tip of the red giant branch, there's a kind of a constant relation, the luminosity temperature relation. You said in one band it's constant and in the other band there's a slope. What's the origin of that difference? Is there a physical origin? Or?
Yeah, so there's actually, if we look at globular clusters in the Milky Way, we can measure the spectroscopic abundances of those stars. In the I band, the bolometric correction is essentially canceling out any difference in the luminosity. And so in the optical, when the metallicity is the optical, you actually have a fainter star. In the infrared, the radiation is redistributed due to opacity effects. The metallicity, the abundance, higher abundance stars are scattering the radiation. Similar effect to dust, but it's in the atmosphere of the star. And so more of it's redistributed in the infrared, so it goes up. But it's very well empirically constrained. So, if you measure spectroscopically what the abundances of these red giant branch stars are, it tracks identically with the photometry. So that's another advantage of the TRGB, is that empirically you can calibrate any metallicity effect. And for the Cepheids, because you have an intrinsic temperature effect, which is also a color term in the PL relation, and you're correcting for dust, and you have to do these artificial star corrections. You get those wrong, you get the other two wrong. It's just much more challenging for the Cepheids. But the TRGB, we see this effect of metallicity. The stars are increasing in their luminosity in the way that we would expect. Empirically, again, we can just deproject them. We're just measuring the luminosity for these stars, and we have hundreds of them, in some cases thousands. So statistically, it's a very well measured quantity.
Okay, thanks. So also you said that the Cepheid, the SHOES project, they made some measurements of distances, and then they reanalyze their distances, and they find a different answer. So I'm sorry if I missed this, but what exactly was the problem? What's the difference between their analysis in 2016 and 2019? Do you know?
They don't really say. I think they a different person reduced the data. And they don't make it actually really clear in the papers. You sort of have to know. So if you compare the distances given in the table in the 2016 paper with the distances given in 2022, then you calculate those distances. That's where it becomes clear that there is this offset. But I think it was an improvement in the analysis, and might even have been the program that they use. But they don't discuss this explicitly.
Okay. Okay. So any questions? Anybody? Everyone's very quiet.
I would say I put you to sleep if it was night, but it's morning your time, so I hope I didn't leave you asleep.
I'm surprised. I'm surprised there's no questions. It's odd. I mean, I have more questions, but I don't want to just sort of take your time. So
Go ahead.
So can I just ask a couple more questions? Oh, sorry, there's a question in the chat. So Donghoon Lee, so I wonder if Hubble constant is a function of time in large time scale. He's a graduate student in Pasteur University. So could the Hubble constant actually be a function of time? That's something that's been sort of brought up recently in cosmology communities.
Yeah, so in effect, so the Hubble constant, that measurements that I'm talking about, we're measuring locally in the nearby universe. But of course, there is the Hubble parameter. So H naught is the Hubble constant at time t equals 0, or where the time we're making these measurements. But of course, as you do go out in redshift, that's exactly what got measured when people discovered the acceleration, right? So it is changing with time. And so early in the universe, when you're matter dominated, there's the universe is slowing down because of the presence of matter, and gravity is moving inward. And then as dark energy starts to take over, then as you're measuring objects that are farther away, they're fainter because of the acceleration. So that's exactly what got measured in the first in the discovery, and now as people are refining the measurements of the expansion. But what we're measuring is time t equals 0.
So I have a question related to that. So you measured something so you assume that the geometry of the local space-time is flat, or local space, I should say, not space-time.
No, we're just measuring literally velocities and distances, no assumption. Now, if we observe more distant supernovae, then yes, we have to correct for cosmology. And so there is in the sample, a handful of galaxies, maybe a dozen, that are far enough out that you would make a correction for cosmology. But there's no difference whether those are included in the sample or not. But for the nearby sample, you don't have to worry about it. It's just negligible.
Okay, but I mean, by measuring a distance, you write down a distance redshift relation, right? So you have to assume that light's traveling in straight lines. So that's where the geometry assumption comes in.
Well, as I said, when you go farther, you're actually seeing the effect of the, lambda, and that you'll see the bending of the Hubble diagram. But it is, approximately linear locally, and the effects of cosmology are negligible when you're measuring at these distances, sort of out to 40 megaparsecs. Well, 40 megaparsecs, you probably have a small correction, but it's couple percent at most.
Okay. So any questions? Okay, I just have one more then. So do you think, so can I get like a quote from you that there is no Hubble tension? What's your personal view on this now? Do you have like, because you showed like hundreds of models at the start, right?
No, I remain open. I think this is a question that's going to be decided empirically, but I do think we really need to improve this middle rung, that the statistics just aren't there yet to give you anything like a 1% measurement. I think, I mean, when I was starting to look into the supernova data more carefully, and there are, you know, a couple objects that have very high weight, and it's just, those are dragging the, you know, Hubble constant, they're making the supernova sample fainter. It still could go either way because of the small statistics, but I am probably less inclined to think that this is going to require fundamental new physics when you see what it's based on. But no, I'm willing to be convinced by data.
Yeah.
But I think it is interesting. I mean, lambda CDM is turning out to be very hard to break. I don't really understand that. I mean, I heard a talk today on the DESI results, and you know, when you put in a prior on you know, fundamental physics, and you don't let things just, you know, fill all the parameter space, it's remarkably consistent with lambda CDM. And the BAO observations are, you know, coming in with a lower value of the Hubble constant. And a lot of the higher values are based on Cepheid calibrations. I mean, using the same calibrations as for the Cepheids. So, you know, things like the Tully-Fisher relation, you're looking at a correlation between luminosity and the velocity, rotational velocity of the galaxy, and the scatter is 20%. So you're not going to get a 1% Hubble constant out of something that has a scatter that's that large. And again, systematics that we don't understand, and, you know, evolution of galaxies is more complex than the evolution of stars. The masers, there are only 5 other galaxies that have maser measurements. You know, you compare that to now thousands of type, you know, hundreds to thousands of type supernovae, type 1a supernovae. So the statistics just aren't there. And Myra variables, there are 2 galaxies that have been measured. There's nothing that has comparable precision yet to the Cepheids, TRGB, and JAGB stars. So until we start seeing things at that kind of both statistical precision, large enough samples that you have some, you know, credible statistical uncertainties, and then also that the systematics have been investigated, and that there just aren't that many things that do. And my real hope was with gravitational wave sirens, because it's completely independent of the you know, essentially measuring luminosities of stars, right? It's just completely different physics. And so I think if we're going to all agree as a community that we have a 1% measurement of the Hubble constant, we need to do this in different ways, which is, you know, the basis of our program to do these 3 different methods and develop those. But, you know, we still have to rely on calibrations. We still have to rely on, you know, in terms of the Cepheids, corrections for dust and understanding metallicity and those kinds of things. It's, you know, every rung of every step of the ladder, you have to, if you're going to get 1% overall, you have to have better than 1% anchors, better than 1%, you know, the supernovae that have TRGB and Cepheid distances, and better than 1% in the supernovae themselves. So I don't think we're there yet. And so, you know, Occam's razor might say, okay, the simplest outcome would be, okay, you've measured this with extreme precision, the CMB. Now you've measured it independently with the matter fluctuations in BAO that have nothing to do with CMB. It's calibrated with BBN and other methods. And then you've got TRGB and Cepheids and JGB stars that are coming in at a lower value. And you have the Cepheids and other things that primarily are calibrated with Cepheids, like surface brightness fluctuations, that are maybe they're the outlier. I don't know at this point, but I am less optimistic. It would be really nice, I think, to have new physics, because I think it would tell us something we don't know about the universe, and I think that would be exciting. But at the same time, if we confirm lambda CDM or something like it, that's also really important to do, because if that's what the universe is, then surely we want to measure it. It's not just because we want something more exciting. So I wouldn't, I want to measure it. I don't want to decide in advance. I want to see the data. So maybe not a satisfying answer, but
no,
I'll wait till I see the data.
It's the correct answer. Okay, thank you. So last chance, any questions? You can raise your hand or put it in chat.
Quiet.
Very shy, wow.
Okay, may I?
Yes, please.
Okay, thanks for nice talk. But based on when the Planck data one released, people actually selling point was that compared to the WMAP, omega m is actually much more than the WMAP data. But what WMAP and the Planck measure from the peak is actually omega m h square or h cubic. So at that time, people don't pay attention for the lower value of the h value, but just emphasizing we have more matter, and that means we have less dark energy, so we have longer ages. Nowadays, people's selling point is changed to just say that the Hubble parameter is much lower than what we expect and inconsistent with the others. But WMAP was consistent with all other data for the Hubble point of view, also the omega m for the large scale structure. Now, after that, people change even in the large scale structure, the value for the omega m is based on their calculation, and then it's a switch from the WMAP value to the Planck data. So it looks like we just, as a theorist, we just forced to think about that there should be some tension. But honestly, if we just adopt the WMAP data, and then I don't think we still have any tension, because the Planck data is focused on the large L, smaller angle. And then in that area, we still have a lot of systematic from the lensing effect and all others. So from that point of view, we still have some systematic, and it's I don't know, it's really, as you pointed out, that you more focus on the local observational systematic, but what I'm thinking about is still have the systematic in the CMB, and the worry is even if we have some data from the stage 4 from the CMB, we may have some systematic about the small scale, large L values, and then accuracy will more focus on those secondary effects, and then we may have maybe more misunderstanding about omega m. So
I think it'll be interesting. I mean, I take your point, and I think initially there was this discrepancy between the calibration and WMAP and Planck, and that got sorted out. When you actually compared the common range in L, they eventually agreed well. And I think both with ACT and SPT now, they're coming out with deeper data, more coverage. That's also going to be interesting. SPT has just come out with a new result, and so there is still a way of improving the microwave background, and the polarization measurements, I think, are going to be also really important. But I take your point. I think everyone now looks to Planck as that's the that's the final view of things, and because of the degeneracies, there may be room for things to move a little bit.
Mhm.
I don't know, but you know, it might not end up at 67.4. It might be more like 68 or 60, well, 69, you know, even BAO is not getting, but I think it will improve with time, and we'll see. But there are, you know, I think it's important that the comparisons are made over the same range in L, because a lot of the differences come because you're measuring, you know, comparing apples with oranges, and it's important to make sure that the comparison is done well. And I think, you know, the lensing, you know, a lot of the degeneracies got broken when they were able to measure the lensing of the CMB, and that helped a lot. But we'll just have to see how things improve with in future. But I do think that if you take realistic uncertainties into account, and maybe this answers partly what I guess Stephen Appleby was mentioning, I don't see much evidence for attention right now. I think there is the possibility that the errors have been underestimated, particularly in the local distance scale. And when you see changes in distances and changes in supernova magnitudes that are moving by more than the quoted uncertainty, you know, the Hubble constant may look as if it's not changing with time. The first plot that I showed you, you know, that it's almost 73 all the way across. So it gives a sense that things have been very stable for a long time, but actually things have been moving quite a bit, and they've been moving by more than the size of the error bars. So until I see things that are, you know, really not moving within their quoted uncertainties, you know, I think I would hold off in being willing to say that, you know, there's a 5 sigma discrepancy and lambda CDM is wrong.
Okay, thank you.
Okay, thank you very much. So last chance if there's any questions. If not, I thank the speaker again. Thank you very much. It's a very nice talk.
Thank you for the invitation.
Okay, so we'll close the session now. So thank you everybody for attending. Thank you the speaker again, and bye-bye.
Bye-bye.